Alright, in this video, it's the third video for week 4, we're going to discuss arc length as a function. In the previous videos, we've talked about arc length just in terms of general computation and some notes related to it. Now we actually want to think about it as a function. So first we have to have a C1 curve, and before we go on, I just want to explain this notation of C1. C1 means that it's a curve with a continuous first derivative. Okay. C2, you might guess, is a curve with continuous second derivative, and so it would therefore have a continuous first derivative. Okay. C0, well, that's just a curve. And then you can keep enumerating C, or the excuse me, the exponent on C, and if it's a curve that or it's a C infinity curve, that just means all derivatives are continuous. Okay, something like cosine curve, right? You can differentiate that however many times you want, and you're going to get something that's continuous. Okay, so we have a curve that is C1 parameterized by x of t. All right, so let's just draw this little sketch in here. There we go. That's going to be our curve, and so we have, oops, not a parentheses, I have vector x at A to denote the beginning, and then vector x at B to denote the endpoint. Okay. Now, what I want to develop is a function s of t. Okay, and what this function is going to describe is the distance traveled along the curve from x of A to this variable place x of t. So let's put this variable place in here. Okay, I'm going to call this vector x evaluated at this boundary t. And what I want this s function to do is to trace along this path from x of A to x of t. So that distance should be s of t. Okay, so it's a mapping from R to R, etc. And so my question is, how do we do this algebraically? Well, we might think it's just an arc length, right? S of t is equal to integral from A to t, all right, vector x prime of t. Oh, this is going to be interesting. And then dt. Now, the funny thing is, writing this t is awkward, right? Because, well, we have t in a bound, right? It's our endpoint. So I can't use t in here, but what I'm going to use is a different parameter, and I'm going to call that parameter tau. And really, for our sakes, you can think of it as a dummy variable, and we're just going to say tau is on the domain a to t, okay, which is exactly what shows up in our integral. And so that function there is going to allow us to compute the arc length from our beginning to anywhere along the curve, and again, the maximum value for t. So t is still within A to B, but then tau is just, oops, and I should actually have closed bracket there. Okay. All right. Then, so that's nice as an arc length function. I would like to point out, and this is going to be important in video 6, stay tuned, that by fundamental theorem of calculus part 1, again, that's the one where we said we can differentiate both sides, right? If we differentiate the left-hand side, s prime of t, all right, and then remembering that a is a constant, we actually just end up with the length of vector x prime at t. Okay, so if we end up seeing the derivative of this arc length function, we can replace it by the length of the derivative vector. Okay? And so this is really nice. Okay? We can actually do this method of reparameterization with that tau. Okay? At any point, we can, instead of using a parameter t from a to b, we can talk about that curve c and parameterize it according to its arc length. Okay, so I could take that same curve that I had above. Okay, so I'll try and replicate it to the best of my ability here. Something like that. And what I could do is say, well, this is going to be x of 0, and then I could say, well, if I want to parameterize it according to its arc length, I can have vector x according to s, and then s would then lie in 0 arc length to the length of the curve. Okay, I can do this, and so this is really just s units along the curve if we think about it conceptually. So then this would be x of 1, and that would be one unit along the curve. And then I have to go another unit, and then I'll get x of 2. And then I can go another unit and get x of 3, etc., until I end up at this one, which would end up being x of L of C. Okay. This is very nice, but like I said, it can be very annoying because you actually have to compute the arc length first in order to use this parameterization, which then it's kind of like, why would you do it? But you can do it. Okay. So that's it for this video, and that's really the main ideas behind arc length. In the next video, we'll explore a related but different idea.